hope you're all doing well and staying safe. Thank you very much for joining the webinar today. And my name is Soumik Siddhanta, and I'm the webinar facilitator and an assistant professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is the part of the online Pratidhwani series that the department is organizing. The webinar series is sponsored by Author Cafe. Author Cafe is an online platform that aids with writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with products like Mendeley, Zotero, Orchid, Crossref, and so on. So you can think it like Google Docs, specially designed and developed for the academic community, and much more. So today we are thrilled to have Professor Malla Reddy from IISER Kolkata. So before we talk, before we start, a couple of technical details. Please do not unmute yourself during the talk. And if you have any questions, please type them in the chat box and we'll try to get at least some of them through to the speaker after the talk. So now I would like to request Professor Sajesh Thomas from the Department of Chemistry, IIT Delhi, to introduce the speaker today. So over to you, Sajesh.
Thank you, Professor Soumik Siddhanta. Yeah, Dr. C. Malla Reddy, he's a professor and head at the Department of Chemical Sciences, IISER Kolkata, Indian Institute of Science, Education and Research, IISER Kolkata. His research work focuses on building strong capability in interdisciplinary areas of fundamental and applied crystal engineering. His group is credited for the pioneering work on mechanically flexible molecular crystals and the structure mechanical property relationship. And also they have introduced the concept of self-healing in single crystals. And someone who has worked in somewhat related area, I can point out that starting from his early works on simple observations on bending and mechanically flexible crystals, he has been instrumental in developing this area into a highly advanced topic within the structural science of solids, and now into applications also, some of which he may be talking about today. And Dr. Reddy has graduated in crystal engineering from the University of Hyderabad and took up postdoctoral research at the Institute of Nanotechnology, Karlsruhe Institute of Technology, Germany, 2007 to 2008. Subsequently, he has been a visiting scientist to Karlsruhe Institute of Technology and George August Universität Göttingen, Germany, and University of Bradford and University of Leeds, UK. Dr. Reddy has been awarded the prestigious Swarna Jayanti Fellowship in Chemical Sciences for the year 2015 by the Department of Science and Technology, Government of India. He has published more than 100 peer-reviewed research articles, and currently he is serving as the associated editor for the journal Crystallscom by RSC, and also as the co-editor for Acta Crystallographica Section B. He was an associate editor for RSC Advances during 2015 to 16, and he was also a member of the local organizing committee of the 24th Congress and General Assembly of IISER, the International Union of Crystallography, 2017, which was held in August 2017, Hyderabad. So a very warm welcome, and over to you, Professor Reddy. Thank you.
Yeah, thank you, Sajesh. Thank you, Soumik, and thank you, Professor Raman, and everyone for inviting me. It is an honor to, get back to IIT Delhi. So almost like maybe more than close to 10 years. So 10 years back, I was there at IIT Delhi, and it was a full experience to meet colleagues who are in the department now. So let me share my slides. Yeah, can you see this now?
Yes, it is visible.
Okay, yeah. Wonderful. Yeah, thank you very much. So I'm basically going to talk about the mechanical properties of molecular crystals. And as you all know, molecular crystals have a range of applications, and so very wide range of applications. For some reason, mechanical properties of molecular crystals were only studied in the context of high pressure, in the context of powder compaction in industries like compaction, powder technology, and in the context of pharmaceutical solids. But as we all know, structure determines most of the properties, physical properties. So, for example, melting point is not a molecular property; it is a supramolecular property, right? So, similarly, many other physical properties strongly correlate with the structure. So we primarily focused on developing a strong structure and mechanical property correlation, which view a range of mechanical actions by crystals. So in slides now. So as you all know, I am from IISER Kolkata, so I don't need to introduce you this institute. So you can see our hostels, and then and this is our research complex, and this is our teaching building. So today I'm going to talk about the different mechanical properties of organic crystal. Like for example, the way organic crystals respond when you apply mechanical stress. So I'm going to just briefly introduce this. We have worked on this for a long time, but I'm not going to go into the details, too much of details of this. So, but I'll just briefly introduce you the mechanical response from organic crystals. Mostly we work with organic crystals. Then I will introduce you another interesting phase called rotor phase or plastic crystals. So this phase is not a new one. So people knew this for a long time. In 1950s, people have studied these extensively, but in those days, insights into crystal structures were very difficult to get. So mostly people have studied them in the context of physical properties. In these solids, molecules basically rotate after a phase transformation from static to this dynamic phase. So I will just briefly talk about this, and I will show you some results from a group in recent time. And then I just quickly introduce thermomechanical properties of polymorphs. And for example, pharmaceutical solids have polymorphs like other organic materials. So I'll just show you how thermal properties correlate with the mechanical properties, and then how you can basically understand the thermal and mechanical properties from the point of view of the structure. So very quickly, I'll show that. Then I'll go into the recent finding from our group, self-healing crystals. So self-healing in organic crystals, almost it was not known. Only very recently people tried to do it, but couldn't really do much as compared to other soft materials like polymers and other materials. So I'll show you how this can be achieved in single crystals, and hopefully examples will come out using our methodology. So whenever we think of crystallography, and people were always interested in a very good RTEP diagram, right? So we need to, people were always interested in getting a very good atomic crystal structure, and you need to just have a very good crystal structures, and then so that is what people used to do. People always look for very good crystals, and so it is obvious because once your crystals are of high quality, then you get very good diffraction pattern, and then that would give you a very good structure. So people were mostly interested in very good crystals, and if you have a crystal which has different domains or polycrystalline, then you get into problems, and then your data will be missing. So you don't want those. So people traditionally have been rejecting those, and now we have a large number of crystal structures, 1 million crystal structures in the crystal structure database, and so this is a big milestone. And so what happened to those crystals which are rejected by most crystallographers? People, whenever crystals were not good, so they simply discarded them and didn't care why they were so, right? So, but in recent times, and from our group as well as from other groups, in crystal engineering particularly, people have started looking at these crystals and then started understanding why certain crystals basically are very soft and why they bend or show different mechanical effects. So so the crystals which we normally think are very good for X-ray structure determination may not be always very good for some other application. But some may be very good, some may not be very good. So it all depends on the context. For example, if you take pharmaceutical industry, if your crystals are very, very brittle, they have certain good properties. For example, they flow very nicely. You can mill them and get very nice spherical type of particles. But you may not be able to make very good tablets out of them because they don't come back. For example, if you take sand and then if you try to make a tablet out of it, you will not be able to make it. Simply whatever you do, you will not be able to make a good tablet. So, but if you have a very, very soft crystal, for example, soft polymorph or soft solid, when you mill it, if it becomes like a paste, again, it will be totally a very difficult thing to handle, right? So you need something in between where you have a good particle flow and particle size, and you're able to handle them. At the same time, you're able to compress them into very good tablets. This is one example. So you need to have optimum mechanical properties for these solids. So, but here, very soft solids may not be very good in the context of pharmaceutical solids. But if you go to the recent topic, soft robotics, people here want very soft materials, and they should be able to do many tasks depending on the nature of the job, or they should be able to respond to different stimuli. So in these cases, people are looking for crystals which are basically like very dynamic in the state and respond to the needs. Here in this context, this would be very valuable. And so for example, microscopic devices, you need very small component, and the crystal size of the crystals is ideal for those kind of applications. So if you look at the mechanical properties of organic crystals, most of the organic crystals, when you apply mechanical stress, for example, if you see here, if you stress a crystal, so simply they would break and then they would fracture. So this is the majority of the organic crystals behave in this way. For example, if you see here, so this is one of the polymorphs of a caffeine. Caffeine, we all know, so this is an ingredient in coffee. If you make it one of the polymorphs of this crystal, which grows into thin needles, and then you break it, then simply it basically breaks, and most of the organic crystals behave that way. There are certain crystals which you bend them, you apply the force, so they don't break easily, and they actually bend, and then when you release the stress, so they come back. So these are basically called elastic crystals. So then when you basically apply the mechanical stress, so these crystals bend elastically, and then when you release the stress, so they again revert back, and then you collect the data from these crystals. So simply you see that they have not undergone any change, so they look exactly the same. So these are very these kind of crystals could be very useful for flexible devices. So this was the first example. Of course, elasticity is a very, very general thing, and every material before fracture or before going into the plastic deformation would show elasticity. So it is not that we have introduced the elasticity to molecular crystals, but we have demonstrated the elasticity and tried to relate it to the structure. So this was first example from our group almost like 10 years ago. And now there are so many examples in the literature, and then people have shown different types of applications for these materials. So these crystals are not very rare, but these are not very common as well. So one can even design them, and still it is a challenge, but we are working towards that, and many groups are now actually focusing on that. So there is a third category. So here, when you apply the mechanical stress, so it would these crystals would bend, but then when you release the stress, they don't come back. So that means these are plastically deformable crystals. So the deformation is not reversible here. So that is why we call them as plastic deformation. So that means they are irreversible. Deformation is irreversible. So that is why they are called plastically deformable crystals. So what is the reason for these different, very, very different mechanical response from these crystals? So the answer must lie in the crystal structures, right? The kind of interactions the molecules have among them, and then the way they pack, for example, into layers or into kind of a corrugated sheets or a three-dimensionally interlocked packing. So all these factors would actually determine this. So, but I'm not going into all those details today. But you must know that the crystal structure basically can explain all these properties in crystals. For example, if you take these plastically deformable crystals, so here you have stacks in this direction. So these are like pi stacks, for example. They could be also different interactions, but then in between them you have weak interactions. So then it is like you have A4 sheets, A4 bundle of A4 sheet. Then you push them, so they nicely bend. And when they bend, the sheet bends, so you see this change in the angle compared to this one, right? So here the sheets are basically parallel to these crystals, and that is why you see this kind of bending, and the mechanism can be explained something like this. So then there are other type of crystals. These, as I said, plastic crystalline phase or rotator phase. In this phase, the molecules basically in the solid state rotate. So this normally happens when you take these compounds closer to the melting point, and then the molecules in the solid state basically start rotating after a certain temperature. So these are called plastically. These are very plastic. You can easily deform them because molecules are rotating, and they're very dynamic, and also that means that these interactions between these sheets or columns are little weak here. That is the reason the molecules are able to rotate. So that is why you will be able to push the molecules in different directions. So so there is a book here. So this is an old book. You can look at this book by Sherwood, who is from Strathclyde University. He has done, and many people of his time actually have done a lot of things on these crystals. So then we recently looked at some of these from the crystalline point of view. And if you look at here, as I said, in the static normal crystals, you have rigid molecules sitting in their positions and they don't move. Or they vibrate, but they don't rotate. But if you look at the plastic crystals, the molecules rotate here. And so then when they rotate, when you go from the static phase, for example, this phase to the dynamic phase, and since you are putting a lot of entropic energy into this, so to rotate the molecules, you need energy, right? So then the molecules basically consume a lot of energy, and then that is why you see a big solid to solid phase transformation. So the delta S, the entropy change is here is quite a lot. And then you could have multiple phase transformations. That means the molecules could rotate along one axis, and then if you heat further, they could rotate in much more orientations, or finally they can become isotropic totally, and rotations could basically be activated in all directions. Then you have a isotropic sphere. So then when you go to the melting temperature, and then this delta S for the fusion, so is very small compared to the solid to solid phase transformation. So this can be useful for in many applications. So these properties will be useful for many applications. For example, if you want to use them for barocaloric effects, that means basically like coolants. So you can basically do cycles here using pressure, and then you can basically take the energy into the material and release the energy out of the material. So that can allow you to cooling kind of applications. So here, since it is only a rotation, so it is not very difficult to do if you are able to give the energy. And then this entropy change is normally for this is very small compared to this one. So these are all characteristics for these materials. So we studied three examples recently, and so these are simple aminoboranes. And if you see the structure of all these compounds, it's very similar. So you have 3 hydrogens here, you have 3 fluorines here, 3 methyls and 3 methyls, and then you have 3 hydrogens similar to this, but you remove one of these methyls and then put a hydrogen, then you get this compound. So they are very similar. The shape is very similar, but if you see the melting points are very, very different, right? So here this is so here you have a polar bond, so that forms a dihydrogen bonding. The properties are very different. So here in these two cases, molecules rotate and they form a plastic state, and that is why you can deform these crystals into many shapes. And they behave like metal wires almost, but this one, since you have hydrogen bonding here in the crystal structure, so you can't bend them in many ways. Simply they break. If you apply on one of the faces, they bend, and so you can even pull these crystals, the plastic crystals, as you can see here. You can also compress them. This is not very common for organic crystals, and you can also make thin rods out of it, like plates by pushing them, and you can even make thin films by pushing between 2 plates, and you can even twist, and then you can go on making different shapes out of these crystals. So you can even take 2 crystals and then push them to just basically kind of do a welding. So as you can see here, you push them, they stick to each other very nicely. So this is something like hot mechanical welding, right? So this is in this happens only in these 2 crystals where you have molecular rotations after a certain temperature, okay, above room temperature. So behave like plastic crystals. If you go to lower temperature, then they become static, then they don't behave like that. The mechanical properties would not be same. But in this case, you don't have the molecular rotations, although everything looks very similar. So because you have a strong dihydrogen bonding interactions between this NH and BH, and then they lock the molecules, so that is why you don't have similar mechanical properties here. And further, if you look at the structure, so you can have slip planes, you can slide the molecules in different directions. So that is why these crystals, when the molecules start rotating, become very, very plastic. So this we could explain using the crystal structures and then interaction energies among the molecules and so on, just to present the difference between the two classes of these materials. So here you can see different shapes that we made from the plastic crystals. So another aspect, as crystallographer, you would always want to know whether they would be still crystalline, right? Or are they really solids? Are they like proper solids or not, right? So then would you expect them to have the same structure? So we were obviously curious to know the structure. So then what we did is we pulled a crystal, and about I think this was about 20% elongation, and then we cut a small portion, and then we put it under diffractometer, and then we saw a reasonably good diffraction pattern, and then we could even get the full data, and then could even solve the structures. So these are approximations. The quality of the data is not as good as the original ones, but this was very good enough for solving the crystal structure, and which is not very common in organic crystals. So this was something unique, and you can even make a plate out of this crystal by compressing, and this is, I think, something like more than 300-400 this way if you look at it. So I think around 500% elongation. Still we could, by taking a small portion from here and then putting on a diffractometer, so we could still get a structure from these crystals. So that means they are still oriented, and then this kind of films, if we can make from single crystals with high crystallinity, so they could be useful in some applications. So we wrote a review recently establishing the correlation between the structure and properties, and we have basically showed how these molecular rotations can be useful in different applications. So we have written this review. You can look at it if you are more interested in more details, and even the perovskites have been shown with molecular rotations have been shown to undergo these solid to solid phase transformation, and which can be used for barocaloric applications. So this plastic state is not a very it's not very uncommon, so one can actually design them and then try to get the make use of them. So and then we have also studied the correlation between the thermal and the mechanical properties. And so since thermal properties and mechanical properties both depend on the structure, so there should be some correlation, and this is known in other materials like inorganic materials and many other materials. People have shown this correlation, so but it was not done in molecular crystals. So we wanted to particularly look at the polymorphs, pharmaceutical polymorphs, and so we have recently looked at some polymorphs in collaboration with the Chinese group, and so this is basically pharmaceutical compound, acetate of a pharmaceutical compound, and it has 3 polymorphs, and it has completely 3 different types of crystal structure. And then you can see that elastic modulus actually increases with the increase in the decrease in the thermal expansion. So for these materials, and we have looked at 3 forms, and then as you can see here, so here the expansion is in anisotropic, and here it is more isotropic, and here it is kind of a negative thermal expansion. So here the expansion is very less, and here it is moderate, and it is very high here. And also that too, it is anisotropic, and then we see a very good correlation between the mechanical properties as well as thermal expansion. If the thermal expansion is negative, then your elastic modulus is high. If your thermal expansion is positive and it is more isotropic, then you anisotropic then if you have more thermal expansion, then it is basically kind of a soft material. So and so then we have been studying various types of
organic crystals. So at some point, we also looked at the thermosalient crystals, which basically like jump because of the sudden phase transformation when you heat them. And so if when you cool down, then they can also come back. And this is another example where we used a photochemical reaction, polymerization reaction to bend the crystals towards the light. But I'm not going into the details of this. So I will basically talk about the last topic. So recently we have ventured into this topic serendipitously, and we were, as always, we study the mechanical properties. So we were interested in mechanical properties when we were playing with the crystals. So my student basically got into this. So as you all know, self-healing is very common in nature, right? So our bone, when it fractures over time, basically it heals. The mechanism here, there are different types of mechanisms. And then in plants, then you get white excretion from the plants when you damage them. Then within minutes, the regions basically heal. And even in the insects, people have studied the self-healing when the parts of the, some parts basically get damaged, so they heal themselves. So people have taken, inspired by these natural materials, and people have been designing and studying the soft self-healing materials. And for example, if you take, and people have looked at many soft electronics and then even polymers. If you look at the polymers, which are, if you take some soft polymers, so then you can basically observe the self-healing. For example, if you see here, you cut the polymer, and then over a period of time, so it slowly heals. And then you have elastomers, and these are also very soft. And then when you cut and then put them together and press, after some time, you see that they heal and then get the same strength as the previous strength that they have in the pristine material. And there are also many polymers, and people have been studying all this. And so all the most of the reports that are in the literature have very soft materials. And the other thing is that most of them are actually amorphous. And so observing self-healing in organic crystals or in any type of crystals has been a big challenge, and not much research has been done so far in the crystalline materials. So, and people have been in the polymers and other materials. People also have engineered different, kind of materials with particular strategies. For example, in polymers, people take put some micro capsules with basically a material, and then they also embed the catalyst into it. Then when you have a crack, so then this crack run through the material and basically exposing the both the catalyst and then these chemicals in the microcapsules. And then when they come out, then there would be a reaction, and then that would fill the cracks. So these are different mechanisms people have been looking at in other materials. But in single crystals, there are very few reports, and most of them use either solvent or heat or something else. There are, you can count on the fingers. So this is one of the macromolecular crystal in solution. So for example, if you put it in salt solution, so they basically expand, and then you would see the cracks, and then again you change the salt gradient, and then again they basically shrink and then heal. So this can be done repeatedly, and then you can get nice crystal structure, nice diffraction from the healed crystal. But as we all know, healing crystals in solution is not a really that big deal. So so it is not easy to observe self-healing in crystals, because unlike gels, elastomers, and then tissue, natural tissue, and crystals are very hard and rigid, right? So crystals are hard and rigid, so they are not very soft. And so then diffusion is very difficult in crystals, because you have tightly packed molecules in crystals. And then you can't also engineer by embedding a catalyst or some capsules into the crystals, because they are very tiny. Normally, you grow the crystals in solution. So taking some of the engineering steps, methods from the other materials is also very impractical for organic crystals. So these are the challenges. And compared to all other self-healing materials, organic crystals are much more harder. So these elastic modulus of these, mostly the organic crystals, is in the GPa, right? 1 to 10 or 15 GPa.
but whereas the other soft self-healing materials have like 200 to 500 MPa elastic modulus. So there are few examples in the organic crystals, and this is one of the examples where so this Naumos group have used these sulfur-sulfur bonds in the crystals, and so they put these crystals together, and then they clamp them together with a small stress for about 24 hours, and then they pulled them back, and then they found that they could gain around 7% of strength. So this is a very, very tiny basically attraction between the particles, but so this is called self-healing, and so this is how you see in the organic crystal. So it's very tiny. And then they found another example where they have about 60 to 70% of the healing, but as you can see here, so you have a big crack here, right? So this is one of the best examples, but you still have a big crack, and the crystal quality also goes down. So for all practical purposes, this would be it would not be very useful, although you see that this is a very soft material. Again, it is, I think the elastic modulus is around some 5 MPa for this crystal, and then when you clamp, obviously these will stick to each other. So this is what has been shown in molecular crystals. So while studying some of the crystals recently, my student Surajit came across this particular bipyrazole type of molecule, and which crystallizes in a non-cytosymmetric space group. And then he observed that when you mechanically crack these crystals, as you can see, you develop a crack, and so then when you release the stress, so they go back and then heal in a very clean manner. You don't see any crack here. So you release the stress, so they come back, and then so this is actually taken with a high-speed camera. So the video is basically a very slow motion of the actual movement. So you see a very clean crystal once you release. So this is basically a self-healing, and the crystals also when you release the stress, when you crack it and then release, the crystals also actually try with force to come back to each other. They come and then get attracted. As you can see here, it healed. You can see a little crack here, but in most cases, if it works very well, you don't see any crack at all. So here again, the crystals basically come back and then hold. So you just basically push it little here. So then when it is enough force, then basically it jumps and then catches each other. So then it basically works very well in these crystals. So then we wanted to know why they are coming back. So then we pushed one crystal closer to this after cracking. So then as you can see here, so when it comes closer, so the distance between them is about 50 microns here in this case. Even when they are apart, so basically they come together and then basically try to heal. So as you can see here, and you make a crack and then release the stress, so they come back on their own. You're not pushing them in the other direction, and then heal in a very, very clean manner. So, and if you basically press the crystals between using the forceps, again you can see the healing. You press a crystal from the top, you see a big crack here, and then when you release the stress, and it heals completely, as you can see in this video here, which is a slow motion again. So but if you do it in real time, you don't see even, so it just happens very, very quickly. So this is the real time, and then this is the slow motion, right? So then we wanted to see, like, under microscope, we could not see any crack. Then we also looked at it under SEM. Then we did not find any crack, and even under SEM with high magnification. But when you here again, you can see this is same crystal, and you don't see anything. But when we don't have a very flat crack, linear crack, then we saw that most of the time it is not healing very properly, because you probably have some debris in the middle, and crystal is not able to close the gap. So that is the reason sometimes you don't see a very good efficient healing. So we looked at the crystal structure. We found that you have water chains in this, but water is not very important. What is important is you need a polar crystal structure, and and then these crystals also, as you can see here, see they are very stiff, 8 GPa elastic modulus on one of the faces, and then on the top 15 GPa. And compared to other materials, these numbers are very, very high. So that means they are very, very stiff compared to other materials like polymers. You need a lot of stimuli or takes a lot of time. So this is in milliseconds, that what we see here. And what is the origin of attraction here? So we wanted to study it. Then what we did is we broke a crystal, we cut a crystal, and then we did a KPFM, Kelvin probe force microscopy, which can basically map the surface potential. And we found that the average surface potential is around 4.72 volts on one of the crystals. And then and we have taken several different crystals and then basically checked. And we have also basically pushed this crystal out instead of basically cutting. And even in that case also we saw the surface charges, but in some cases we have seen positive charge, and in some cases we have seen negative charge. So we see either totally positive or negative. That means when you cut the crystal, on one surface you have positive charge, and the other surface you have the negative charge. So that is what we basically thought. And then we thought, okay, we take a crystal which has a crack, without a proper healing, and then you do the KPFM here. If you have opposite charges, then you should see a gradient. So then that is what we have seen. One side you have negative charge, and the other side you have positive charge, positive surface charge. So this says that the crystals are able to attract because you have some electrical charges. So we saw that even in ceramics. So for the cracked ceramics, piezoelectric ceramics, people have actually reported that, but nobody talked about the attraction or something else. But this was the only clue that we had to explain this entire mechanism. And so then we took a completely self-healed crystal, and then we did not see any gradient here across the crack. So that means once it heals, then you don't have any permanent charges, or at least the gradient you don't have on the crystal. You have something, but it is not basically a gradient. So that means it is able to heal properly. So then we have also done the PFM, and which is typical for the piezoelectric materials. Then we proved that this is a piezoelectric material, and so then we also took these crystals and then have done the diffraction on the neatly healed crystal, and then we saw that they are as good as the original crystals. You get beautiful diffraction pattern once they fully heal. But if you take a crystal with some crack, then you see some split peaks because the domains are not fully aligned here. Then we wanted to understand in the fully healed crystals the local order. In the X-ray you don't get a very good idea about the local order because it is an averaging technique. So you need a spatially resolved technique to find out the order. So then we collaborated with one of my colleagues here in IISER Kolkata, and then we used the Muller matrix birefringence spectroscopy. And here we could see that if it is fully healed, the order is very, very good. So this is a pristine crystal, and you look at this number, don't worry about it. So this is called linear diatonation. So this is one of the quantifying methods. Basically, this is a parameter which quantifies the local order in the crystal. So if you see here, for the pristine crystal, it is just above 0.2. Okay, so then when you take a fully healed crystal, it is just below 0.2. But if you take a cracked crystal, you see it very, very low. So this is 0.05, this parameter. That tells you that, so these crystals basically, once they don't heal properly, so then the local order basically it drops. Once it heals fully, then you have a very good order. So this we have done. And so I think I will skip this. And so what is the mechanism? Why do these crystals heal? So with this mechanism, I would close my talk. And if you look at here, so in the piezoelectric crystals, normally you have molecules with polar molecules, all of them aligned in one particular direction. So here, all the dipoles are aligned in one particular direction. And when you make a crack here, and you basically generate the two surfaces with the opposite nature. For example, if you see, all the tails are basically open here, and all the heads are open here. As you can see here, so if you have negative charge on the head, then this entire thing would be negatively polarized, and this entire region would be positively polarized. So this is what we would see from the KPFM data, and we could see clearly the charges. That is why when the healing is not very clear, you see one side negative and one side positive and negative charge. So that is what you see. And since they are piezoelectric, when you press them, they generate the fully elastic. When you release, then the elastic, then there should not be any charge on the material, even though they have opposite ends on that. So then the charge that you have is huge actually. That is why you are able to attract. And but if as grown crystals don't attract each other that much, so that means there is some fatigue here. There is some amount of plasticity in the crystals. So that is why there is some remnant charge. So that is why the crystals actually heal. So you have hydrophobic zones, and we have done a lot of work on plastic crystals, plastically deformable crystals. We know that whenever you have large hydrophobic zones, you will see some permanent deformation in the crystals. So this is, for example, this is one of our earlier work where we have studied the plastic deformation in plastic bending in hexafluorobenzene crystals. So from this, we know that there is slight plastic deformation. That is why you have self-healing in these crystals. So we have, using this understanding, we have again screened the literature, and then we found some piezoelectric crystals, and we found self-healing in other materials as well. So now we have several examples in this direction. So this tells that there is a lot of scope for developing this. But you can ask if all the crystals which are piezoelectric are going to self-heal. So that is not the case. For example, if you take this histidine, L-histidine, so you don't see any attraction between the particles. So it is absolutely normal like other crystals. You don't see any attraction, although this is a very good piezoelectric material. So then what is the reason? Then our further studies, which we have not yet published, shows that you don't have a drop in the order here. That means it doesn't have any fatigue once it develops. So it simply cracks. It is an elastic cracking, basically, brittle fracture, elastic brittle fracture. If you have slight permanent deformation here, so then you would have slight distortion. So that would actually leave some permanent charges on the surfaces. So this, again, using the Muller matrix, we could, from the collaboration from our physics colleague, we could say this. So we have not yet published this, but we will do it at some point. So with this, I close my talk, and thank my students, particularly Surajit, who has done this self-healing work, and Susoban has done the mechanical property work, and then other people are working on different things, and my pharma students and my collaborators, and so Nirmala and Banu Bhushan Katua from IIT Kharagpur, who has done the piezoelectricity work for our self-healing crystals, and then funding from DST and SEB and CSR and CIPLA for also consultancy projects, and IISER Kolkata finally for all the facilities and posting me the job there. Thank you very much.
So thank you, Professor Reddy, for the very insightful and stimulating talk. Okay, so I would like to request Professor Thomas to conduct the Q&A session now. Over to you, Professor Thomas.
Thank you, Dr. Soumik. Those of you have any questions, please type down in the chat box, and I can ask it for you. Please type down your questions. In the time being, maybe I'll start with a question.
Yes.
Yeah. One thing. Yeah. First of all, yeah, it's a beautiful presentation and beautiful work. And regarding the last section, the self-healing, based on the very last slide, you mentioned about histidine crystal not being self-healing, and is it because of at the local domain level on the surface, at the domain level, we need to have this flexibility, the plastic flexibility to rearrange and heal themselves? That's what you meant?
Not exactly, but plasticity, some plasticity is required. What I mean is, when you break a crystal, so there should be slight fatigue in the broken tip. So if you have a slight, suppose if you take piezoelectric materials, so when you compress, then you are basically moving the charges, polar molecules, so in different directions. So that is how you are creating the opposite charges. Okay.
Yes.
So if you release, if it is a purely an elastic material, if you release, so then you you would not have any remnant charges.
Okay.
So suppose if the material is not fully elastic, if there is slight permanent deformation, then you would still some remnant charges on the surfaces. Okay, that means if we have slight plasticity, it could be local, just slight distortion, or I really don't know what exactly this means, but if the order is not exactly, it's not perfect. So there are some defects, or some slight distortion, or some, we really don't know that, but there is slight fatigue, and that is what basically leads. So that is what we understand.
Okay, and one more question. Have you been able to, for the actual self-healing crystal, have you been able to, I hope it's a polar space group, something like P21?
I think I don't remember exactly, but it's something like, I think,
okay.
P4 something.
P4221 maybe. Yeah. My question is like, could you measure the piezoelectric current or anything based on
Yes,
did you do that?
Yes, we have done detailed piezoelectricity measurements using piezometer, and we have done PFM, and so we have done a lot of work, but we have not published all that in one paper, but that's going to come later.
Okay, thank you very much.
Thank you.
So there is one question from Dr. Taban Chowdhury. Please let us know whether stabilization or energy minimization plays any role in the self-healing of crystals.
So what do you mean by self-stabilization? So suppose what I say is that when you have broken ends with slight fatigue at the tip, that means there is slight plastic deformation at the tips, but it is not really like some bending or something. So there's slight drop in the order parameter. So then when they come back, and then they basically try to heal perfectly, so that you don't have any remnant charge. So that is, so if you avoid remnant charges, so you reach basically a very good order again. You're regaining some order, extra order once you heal properly. So that is a kind of a stabilization. But for some reason, if they're not able to come perfectly, and if you see slight positive and negative charge, and we see a big drop in the order. So that means it is destabilized when it is not able to heal perfectly. So that is a driving force. So if it heals, so there is a advantage. If it doesn't heal properly, there is a penalty, because your order parameter is going down and you have huge charges, opposite charges. So it is, the charges are driving it to, these imperfections basically are driving it to go into the perfect state.
Thank you very much.
Thank you. And then there is a question from Anupam C. Can a local thermal stress in the crystal domain be the reason for fatigue, eventually inducing self-healing in piezoelectric polymers? Question is about piezoelectric polymers.
Polymers, you mean?
Can a local thermal stress in the crystal domain be the reason for the fatigue, which is eventually inducing self-healing in the piezoelectric polymers? There is a question.
Okay, so I really don't know if the thermal component is so big in healing of the polymers. So in polymers, normally there are different methods. So if you look at some methods, they have some chemicals basically, like A and B. When you mix them, there is a reaction, and they flow and then fill the gap. So probably you're talking about cases where you just cut and then put them together, they heal. So in those cases, mostly it is a diffusion, or you have reactive bonds, bonds like, for example, sulfur-sulfur bonds, they exchange continuously. They are quite dynamic. So then when they are next to each other, so you have dangling bonds, like, molecules are not really stabilized, so you have little higher energy there. So they try to, because you have some mobility there. So all those cases, you have a good diffusion inside near the crack tip. So that is why they are able to basically readjust and then basically go into better arrangement.
Okay.
But as such, I don't think thermal energy is that big factor there.
As a follow-up of this question, and maybe it could be a stupid question, but in case of polymer, we can imagine when you cut the crystal, the solid, what you're cutting, you can imagine dangling board, bonds, just like you mentioned. But how about a molecular crystal? When you cut, you would be breaking the intermolecular interactions only, right? So
yes, that is
the
what
origin
yes.
of this. So origin of this local charge has to come from the dipolar contribution, molecular dipolar contribution locally. So what do you think the origin of the charges are?
Yes, origin of the charges is basically the molecular you have polar structure, right? So all the dipoles are oriented in particular direction. So then they are going like this. So you cut, then so then on one end you have these dipoles, which are all are like you are opening up the positive parts of the molecules, and then on the other end you are opening up the negative ends of the molecules. So then because of the distortion inside the bulk, very close to the tip, so the packing is not perfect. So that is disturbing the thermodynamically stable position. So that is why you have more charge. So that is simply like if you take the piezoelectric material, if you disturb the thermodynamic positions and move them away, so you have the charges. So it exactly happens, the same mechanism, but since your polar direction is this, so then when you cut, so then obviously your charges are basically opposite in two ends.
It's like okay,
so
orientational. Okay.
Yeah.
Okay, thank you. Tarak is here. I think you can ask directly if you want, or I can read out. Okay, Tarak's question is, thanks for the fantastic talk. This is Dr. Tarak Kharmakar, who recently joined the department.
Okay.
So, and thanks for the fantastic talk. I was curious about a typical solid-solid phase transition for a plastic crystal. Does one solid transform through a liquid phase to another crystal? Thanks. So his question is whether the solid-solid phase transition happens through a liquid phase.
No, it is, you can't say it is a liquid phase. So suppose if you have a lattice with molecules which are static, then you give them enough energy, so they are able to free some of these bonds and then start rotating in the same position. So everything is rotating in, but they are not moving. Liquid means you need to move these molecules in, isotropically almost, right? But at least, you should be able to move them away from their lattice positions. But here, they are sitting exactly in the same place. But only the freedom that you have is a rotational freedom, but no translational freedom. You have a little bit of translational freedom, but that doesn't, qualify them to be liquids. But it is more like a crystal.
Center of masses of the molecules may be still forming roughly the same kind of lattice.
Exactly.
Right?
Exactly. Okay. That's the right way to put it. Exactly. They are not moving away. So that is why you can't call them like a liquid. So people initially, in those olden days, people called, using different terms like, to relate them to the liquid crystals. Okay. So something like that. But later people realized that since they give very good diffraction, that means the molecules are sitting quite well in their positions. So that is why you can't call them as liquids. But when you basically melt something, then suddenly they gain all the freedoms, right? So then here they gain only part of the freedom, only rotational freedom, not translational freedom. So that is why this entropy change is also very big. So in the solid to solid, normally it is quite big. So normally you don't see that much energy change for solid to solid.
Thank you. Thank you, Professor Reddy.
Yeah, thank you.
As okay, I think Professor Soumik Siddhanta has a question, but I think if you want, you can ask yourself.
No, you can go ahead.
Okay, so Professor Soumik Siddhanta is asking, can these self-healing crystals reject impurities or adducts by themselves? For example, if you poke a pin, can the pin be ejected by the crystal?
Yeah, so I think, see, we have not seen that, but I think at the macroscopic level, I don't know if that is going to happen. But these are quite, dynamic in some sense. So, but I really don't know. But at the surface, I can tell you, like, when you do this in liquid, for example, so then they still come together. Even if you make a big crack, the steam come together and they can yield efficiently. Okay, so as efficiently as when you do this in air, on a plate, glass plate. So this some way tells that they are able to basically push out the liquid and then come back, and then they heal perfectly. Like you take the crystal out and then you don't see any difference. So in some, at least at that place, they are able to do it. But when you push them with a needle, and if it is a crack, normally it heals. But I don't know really if you make a dent. For example, nano indentation, if you do, I don't think that it can happen. But I'm not really. So only a few examples we have. We have to wait, I think.
Okay, thank you very much. And is there any other questions? If not, over to you, Professor Somik Siddhanta.
Yeah, thanks, Sajesh. So I'd like to thank Professor Reddy once again for agreeing to give this webinar, and also we hope to host him. We hope to host you again, physically in our institute, sometime when all these COVID things goes away. So hopefully we can, invite you directly, physically to our institute,
Thank you.
hopefully very soon. And before we disperse, I think I'd like to thank Professor Anil Elias, our head of the department, and Professor Ram Ramaswamy for their constant encouragement, and also Professor Janakiram and Professor Biswarup for co-organizing this webinar series along with me. And on behalf of our department, we would like to wish you good health in these difficult times. Please take necessary precautions and stay safe. And we hope to see you all again soon. So have a great evening. And thanks again, Professor Reddy.
Thanks.
Please take care.
Thank you very much. Thank you.
Thank you. Bye.